Director, Indian Institute of Science, Bengaluru. Padma Bhushan, Dr. Mrs. Manju Sharma, Chairperson, Governing Board. Shri Alok P. Sri Ramji, Vice Chairman, Governing Board. Other members of the Governing Board, Shri Vijay Sardana ji, Techno-Legal Advisor, RAC members, Their Excellencies, the Ambassadors and High Commissioners, Senior Diplomats from the Diplomatic Missions in India, Dr. Mukul Das, Director, Shri Ram Institute for Industrial Research, invited dignitaries, ladies and gentlemen. I, Dr. Meenu Talwar, Scientist, Shri Ram Institute for Industrial Research, take the privilege to welcome you all to this 56th Shri Ram Founder Memorial Lecture. In the honor of our illustrious founder, Lala Sir Shri Ramji, the first Founder Memorial Lecture was organized in 1965. Since then, every year lectures have been delivered by eminent personalities of the field of science and technology from both India and abroad, thereby making this lecture a major scientific event of the country. A great visionary of his time, Lala Shri Ramji, realized very early that indigenous production of materials will be the foundation of growing Indian economy. Lala Shri Ramji was amongst the first generation of Indian industrialists after independence who built a huge industrial empire. He could foresee the requirement of a strong and self-reliant R&D base in the country and thereby founded Shri Ram Institute for Industrial Research in 1947, which has been operating as a self-supporting institute and continues to provide valuable technical support for growing and ever-changing industrial needs. Today's Founder Memorial Lecture is being delivered by Professor Anurag Kumar, Honorary Professor, Department of Electrical Communication Engineering and former Director, Indian Institute of Science, Bengaluru, known globally for his excellent work in the area of communications networking. In today's lecture, Professor Anurag Kumar will share his vast knowledge and experience on the subject with us through his lecture entitled Cyber Physical Systems for Industry 4. Now we will begin the program by lighting of the ceremonial lamp and seeking blessings from the Almighty by offering prayers. I request Dr. Mukul Das, Director, Shri Ram Institute, to escort the dignitaries to the dais for lighting the lamp. The dignitaries are Professor Anurag Kumar, Dr. Mrs. Manju Sharma, Shri Alok B. Sri Ramji, and Shri Vijay Sardana ji. May the light of this lamp enlighten our path of progress. As per ancient Hindu tradition, it is customary to invoke Lord Ganesha's blessings to mark the beginning of any landmark event. Keeping in line, our scientist, under the guidance of Dr. Lakshmi Rawat, will now present a Ganesh Vandana to pray for prosperity and wisdom.
उदकमङ्गलम् अग्निमङ्गलम् वायुमङ्गलम् गगनमङ्गलम् सूर्यमङ्गलम् चन्द्रमङ्गलम् जगत्मङ्गलम् जीवमङ्गलम् देहमङ्गलम् मनोमङ्गलम् आत्ममङ्गलम् सर्वमङ्गलं भवतु सर्वमङ्गलं भवतु गणनायकाय गणदेवताय गणाध्यक्षाय धीमहि गुणशरीराय गुणमण्डिताय गुणेशानाय धीमहि गुणातीताय गुणाधीशाय गुणप्रविष्टाय धीमहि एकदन्ताय वक्रतुण्डाय गौरीतनयाय धीमहि गजेशानाय भालचन्द्राय श्रीगणेशाय धीमहि एकदन्ताय वक्रतुण्डाय गौरीतनयाय धीमहि गजेशानाय भालचन्द्राय श्रीगणेशाय धीमहि चतुराय गान प्राणाय गानान्तरात्मने गानो सुखाय गानमत्ताय गानो सुखमनसे गुरुपूजिताय गुरुदेवताय गुरुकुलस्थायिने गुरुविक्रमाय गुह्यप्रवराय गुरुवे गुणगुरुवे गुरुदैत्यकलक्षेत्रे गुरुधर्म सदाराध्याय गुरुपुत्र परितात्रे गुरुपाखण्ड खण्डकाय गीतसाराय गीततत्त्वाय गीतगोत्राय धीमहि गुणगुल्फाय गन्धमत्ताय गोजयप्रदाय धीमहि गुणातीताय गुणाधीशाय गुणप्रविष्टाय धीमहि एकदन्ताय वक्रतुण्डाय गौरीतनयाय धीमहि गजेशानाय भालचन्द्राय श्रीगणेशाय धीमहि एकदन्ताय वक्रतुण्डाय गौरीतनयाय धीमहि गजेशानाय भालचन्द्राय श्रीगणेशाय धीमहि
thank you, Shri Ram Institute Vandana Group. To pay homage and tribute to our founder, may I request Dr. Mukul Das to garland the bust of Lala Sir Shri Ramji. May I now request Dr. Mrs. Manju Sharma to present a bouquet to today's speaker, Professor Anurag Kumar. I now request Dr. Mukul Das to deliver the welcome address.
Our esteemed guest speaker for the afternoon, Professor Anurag Kumarji, respected Chairperson, Padma Bhushan, Dr. Manju Sharma-ji, Shri Alok Shri Ramji, Vice Chairman of Governing Board of Shri Ram Institute, Shri Vijay Sadana-ji, Advisor to Shri Ram Institute, members of the Governing Board of Shri Ram Institute, members of Research Advisory Committee of Shri Ram Institute, distinguished guests, dignitaries from various embassies and high commissions, faculty members and scholars from universities and research institutions, members of electronic and print media, my dear colleagues and their family members. A very good afternoon to all of you. It is indeed a great privilege for me to welcome each one of you to this August gathering to be the part of the 56th Shri Ram Founder Memorial Lecture. It is after a gap of 2 years caused by the pandemic, we could come together to celebrate this Founders' Day. These 2 years have affected all of us, in fact, the whole world, at individual levels and on institutional and national levels as well. We are happy that the past is now gone by and mankind is looking forward to building a new future with the hard-learned lessons of limitations and human resilience. Today, we pay homage to our illustrious founder, Sir Shri Ramji, on the eve of his 138th birth anniversary. He was a visionary, well beyond his own times, a successful industrialist and an institutional builder, who initiated and founded several academic and cultural institutions, including our own Shri Ram Institute for Industrial Research. And this was all at that time when our nation had received its independence and was transiting to the new beginning. Even in those early years, Sir Shri Ram, who was fondly called Lalaji, foresaw that if India has to progress and become self-reliant, we need to innovate and apply technologies to areas that touch our day-to-day living and those which concern the common man. That is the spirit that still embodies Shri Ram Institute. Lala Shri Ram vision was further developed in the later years by the able leadership of Dr. Bansidhar, taking Shri Ram Institute to greater heights, which is now continuing to be nurtured under the dynamic leadership of Shri Alok Shri Ramji. The year just gone by was the year of upturn from the pandemic effects. Now we have weathered the rough patch and are looking forward to greater growth on all fronts. Pandemic has taught us new lessons: how to meet and work remotely, how to aid others in their needs, and how to remain optimistic even in the midst of uncertainties. Even during the lockdowns, I would like to mention that Sri Ram Institute had continued to provide its valuable essential services, be it testing of medical goods or providing sterilization services for the healthcare goods. Let me put on record the appreciation to all the staff members who had dedicatedly rendered their services in those difficult days. During 21-22, scientists of SRI have published 10 research papers in high-impact fact journals, including The Lancet, Current Genomics, Journal of Food Science, etc. They also contributed chapters in 6 books and were granted 1 Indian patent and applied for 3 other patents. Some of the noteworthy awards received by SRI scientists during this particular year are as follows. Dr. Mukul Das, Director, received Lecture Award in the field of toxicology by the National Academy of Sciences, India during 2021. Dr. Panklesh Arora, Scientist, received the Phenomenal She Award by the National Bar Association during 2021. Mr. Dushyant Singh, Scientist, received ESDA Young Scientist Award by Environment and Social Development Association, Delhi, during October 2021. Dr. Aarti Man, Scientist, received the Best Oral Presentation Award at International Conference on Materials and Technology, organized by Mahatma Gandhi University, Kerala, during December 2021. Ms. Khushbu Kapoor, Scientist, was awarded PhD degree by MIT University, Noida, during January 2022. I would like to briefly mention about some of the highlights of the individual divisions which are working in our institute. Our Material Science Division during the year have initiated some interesting work, which includes a carbon-based room temperature, hydrogen storage materials, and development of low-cost fuel cells. The division has also developed and transferred technology for UV curable coating for the benefit of rural artisans. Technology Business Incubator, SRI, is implementing a very innovative project valuing 1.63 crores for a 2 megawatt pilot geothermal project generation unit during this year at Manugru, Telangana. The Metals and Mineral Division provided valuable services to industries and gave consultancy with utmost precision, and the group has developed a special composition of all solid chemical formulation for removing deposits on offset printer rollers and have filed the patent for the same. Our GLP certified toxicology and chemical labs are providing safety evaluations for national and international sponsors. This division had successfully developed a process for the conversion of press mud, which is a waste material of sugar production, to fertilizers through biological conversion in about 4 weeks' time rather than taking 8 weeks, and had transferred the technology to the industry. The Environmental Science Group has been supporting Central Pollution Control Board by undertaking studies and data generation of pollutants and air quality monitoring. They were designated as the key resource center under Ministry of Jal Shakti, launched by Jal Jeevan Mission, and organized a series of online training programs ensuring safe drinking water in rural homes. Our civil engineering section had backed a project worth 82 lakhs on quality inspection of the new 6-lane highway under construction of highway at Haryana. The Bengaluru branch of SRI had developed 2 technologies and applied for the patents for the same. In the world which thrives by the energy of partnerships and collaborations, Sri Ram Institute has held hands with some of the organizations. Recently, we have signed an MOU with the Federation of Indian Industries and have formed a consortium with Greenstat, Norway, ventured into an association with ISKCON, and for infusing scientific temper to students, had an MOU with Hindu College. Sri Ram Institute remains committed to the excellence in research and development of new technologies under the able stewardship of our chairperson, Dr. Manju Sharma ji, and vice chairman, Sri Alok Shriram ji, and valuable guidance from the governing board of members and research advisory committee members. Today, we are privileged to have with us Professor Anurag Kumar from Indian Institute of Sciences, Bengaluru, where he was the director for several years and still continues to associate and contribute to this prestigious institute and to the society at large. He will be delivering today's lecture dedicated to the memory of our founder. I'm sure we will be having a very engaging and enlightening time listening to Professor Kumar. Thank you very much.
Thank you, sir. May I now request Dr. Mrs. Manju Sharma to introduce the speaker.
Namaskar. A very warm welcome on my behalf also to all the very distinguished guests. Chief guest, Professor Anurag Kumar. Madam, she has also come, Madam Anurag Kumar, Shri Alok Shriramji, Dr. Mukul Das, all the members of the RAC and governing board, the distinguished participants in this event, and my dear students. It is always indeed a pleasure to attend this annual function of the SRI. I would like to pay my respectful tributes to Sir Lala Shriram on this occasion for giving us this wonderful institute for doing advanced scientific research. On behalf of the scientific community and many of the young people who have joined the institute, I congratulate Shri Alok Shriramji and his team, Dr. Mukul Das, who are carrying the functions of the institute extremely well, and also promoting very good quality science and related to industry and other institutions. I'm indeed very happy to introduce Professor Anurag Kumar, who agreed to deliver this lecture at my request, and I'm thankful to him for that. Professor Anurag Kumar did his B.Tech from IIT Kanpur and PhD from Cornell University. He was a member of the technical staff at AT&T Bell Laboratories before returning to India and joining the Indian Institute of Science, Bangalore. He joined there as a faculty member in the ECE department. He was the director of the institute during 2014 to 20, and now, after superannuation, he's honorary professor. He has published extensively in the areas of communications networking, and distributed systems, and has co-authored 2 internationally adopted textbooks in communication networking and wireless networking. He was awarded the 1977 President's Gold Medal by IIT Kanpur. He received the I.I.Sc. Alumni Award for Excellence in Engineering Research for 2008 and the III Award for Engineering Excellence. He has been elected fellow of all the important and the top academies of the country, including the World Academy of Sciences. During 2005 and 2009, he was the area editor for the IEEE-ACM transactions on networking, and was then on its steering committee. He is the recipient of the J.C. Bose National Fellowship, awarded by the Department of Science and Technology, Government of India. We are extremely happy today to have Professor Anurag Kumar. We have waited for his lecture for the last 2 years, and I really welcome him to deliver this lecture. Professor Anurag Kumar.
Lights. Good afternoon, everyone. And first of all, I'd like to thank Shriram Institute of Industrial Research, Professor Manju Sharma, Mr. Shriram, and Dr. Mukul Das for waiting patiently for almost 2 years. The invitation had come to me sometime in March 2020, but then thereafter the first wave of COVID came and second wave came, and finally I have made it here. So thank you all very much for inviting me and making me a part of your august list of speakers. So without further ado, I'll get into my topic. My topic is perhaps not so familiar to people who work on analytical chemistry and toxicology, which I'm hearing is your main forte. But I also understand from Mr. Shriram that you're getting into areas like AI and robotics and all. This is somewhere in the middle. So I suppose those of you who are probably going to be a part of that new technology might sort of relate to this a bit more. But since I see the word industry in your name, I suppose you do work with industry. You must be transferring technology to the industry. And industry is going to change dramatically in the next few years. And some of what I'm going to tell you in this talk is going to show you how electronics, telecommunication, artificial intelligence control systems are going to impact the industry. And you may be seeing this transformation happening in maybe the next 4, 5, or 10 years. So this particular title has in it maybe 2 parts. One is this cyber physical systems. I'll explain that in the first few slides of my presentation. And Industry 4.0, we say it Industry 4.0, not Industry 4, because 4.0 means that it's a certain sort of certain evolution of the industry. This is the fourth generation of the industry, so we say 4.0. So I'll also talk about in what way Cps technology, I'll shorten this first 3 words into the term Cps, in what way Cps technology will play a role in the industry. I'll then go on to talk about the technical aspects of Cps and the challenges in Cps, and that probably will be enough time for me to finish. Okay, so before I get into what Cps is, I'd like to tell you about a few things that our national leadership spoke about Cps maybe about 3 or 4 years back, just around the budget that particular year. So the Prime Minister, in his speech in 2017 in the International Science Congress, said, One important area that needs to be addressed is the rapid global rise of CPS. There is a need to develop and exploit these technologies in services, manufacturing sectors, in agriculture, water, energy, traffic management, health, environment, infrastructure, geoinformation systems, security, financial systems, and so on and so forth. We need to develop an inter-ministerial national mission in CPS. So this is what the Prime Minister said about 5 years back. Following that, and in the budget speech in the following year, the then Finance Minister said this: combining cyber-physical systems has the great potential to transform not only innovation ecosystem, but also our economies and the way we live. Department of Science and Technology will launch a CPS system mission to support establishment of centers of excellence. Okay, so this was said about 4 years back in the budget speech. Now, before I get on to how the Prime Minister's and the Finance Minister's vision materialized, I'll tell you about what other agencies around the world were saying a little bit earlier. So National Science Foundation, which as many of you would know, is the main funding agency for science and technology in the United States, and has had a major impact on the growth of science and the impact of science on their culture and on the economy, said in 2012-13. They at that time were calling, so what NSF does is, the NSF identifies key areas, and then they call for proposals in those areas from the researchers in the country, in their own country, to work in that area. So they identified in 2012-13 the area of CPS. Cyber-physical systems will transform the way people interact with the engineered systems, just as the internet transformed the way people interact with information. A very key sentence out there, it tells you the distinction between CPS and the internet. The internet permits you to connect information, computers, data, whereas the CPS systems will connect the physical world through the internet with the physical world and control. However, these goals cannot be achieved without the rigorous systems engineering. The CPS of tomorrow will need to far exceed the systems of today in capability, adaptability, resiliency, safety, security, and usability. A lot of words out there, each one of them very important words, each one of them requiring a career in research to be able to make an impact on. Okay, so NSF has already defined a vision for CPS as far back as a decade back. Sure enough, a couple of years later, after the Finance Minister's, in fact the following year, after the Finance Minister's speech in 2018, budget speech, the DST, Department of Science and Technology in India, announced a major mission called the National Mission on Cyber-Physical Systems. And in fact, we in I.I.Sc. were involved in defining some of the goals of this mission. And they announced a huge program. This is about a $500 million program in promoting this research area in India, across the universities and in the industrial sector. And this was the call for proposals. So just like NSF called for proposals in 2012-13, DST called for proposals about 7 years later, and this was the 3,500 call for proposals. This call for proposals is already closed now. I think the 2020 was when the proposals went out and the proposals came in and selections were done. Okay, so I've given you some idea of what the national leadership has thought about this area that I'm going to talk about. I've given you some idea of the international importance of this area, and I've also given you some of the money that large amounts of money that the government has put out to promote research in this area, and now you'll find most of the IITs and NITs and all, and I.I.Sc. working in this area for the last couple of years. Okay, so what is the CPS and what is Industry 4.0 Internet of Things? Let me explain that in some sort of high level, in a high level description. Okay, now any CPS system, I'll keep shortening the long thing into CPS, is concerned with the physical domain. It could be lighting in this hall, it could be ventilation in this hall, it could be the safety in a factory, it could be the yield of a farm, it could be the performance of an engine in a motor car. So it could be something as small as the engine in a motor car, something as big as the entire city's water distribution system. So there's some physical domain. Okay, so underlying any CPS system is a physical domain. For example, civil infrastructure, you might want to monitor the structure of this auditorium if it is in a place where there's a lot of earthquakes and seismic activity. Farm, factory, urban water, air, traffic. So all of these are examples of physical domains that a CPS system could be concerned about. Okay? What comes next? Well, if you want to observe a physical system, you have to go and instrument it. You have to put sensors in it. You have to put actuators in it if you want to modify it at some point. So these sensors and actuators, connected by communication networks like the internet, like Wi-Fi, like other technologies, I'll talk about it a little later, form what is called IoT. Now, you hear so much about IoT in the media nowadays, in job advertisements. Well, IoT plays this role. IoT is sort of the layer above the physical domain, where you're connecting into the physical domain and you're connecting up these touch points through a communication network. So that is IoT, Internet of Things. Rather than Internet of Information, or Internet of Things connecting to the physical world. Above this, we have the CPS system itself. What does CPS do? The CPS system is gathering information, making decisions about the information. That's the inference aspect. It is inferring, say there's a fire, the illumination is too low, or there's a crack appearing in this building. That is the inference and decision making. Decision making would say, okay, go and do this thing, send out a troop of people to put out the fire. Or you could have control. Control, of course, as you know in industry, is closed loop control. You observe, you modify, observe, modify, that's control. So these three layers, the physical domain, the Internet of Things layer, and the inference and decision and control layer on the top form a CPS. Now, where does the term CPS come from? These are the cyber layers. What is cyber? Cyber is a sort of a popular term which encapsulates communication, inference, and control. That's what the cyber layer is. And physical is the physical layer below. That is the physical domain. Cyber physical system is built from these three layers. Now, I'll come back to it a bit later. You cannot have this by itself. You have to have something else in between. And I'll talk about that as I come to that particular point a few slides down. Now, although it may seem that our leadership and NSF and such organizations have conceived of CPS just about 10 years back, that is not true. In fact, the CPS concept has been around as long as microprocessors have been around. If you're a microprocessor, you can do computer control. So I'll give you an example in the next slide of how Bosch used the system, this sort of a concept as far back in the 1970s for fuel injection in the cars, in the Bosch in the Bosch engines. But the term CPS was not coined back then. The term CPS was coined much more recently. It was coined just about 15 years back by NSF again. NSF then went on to call for proposals about 6 years later. And this term CPS was coined by them in a white paper by Helen Gill and Rajendra Baheti. Okay? Now, so what distinguishes the CPS of the 1970s, where Bosch was concerned about the efficiency of internal combustion engines in the cars, to CPS of today? What distinguishes are the physical domains. You're concerned with very different physical domains than they were concerned about, where it was something much more local, managing a car, managing an engine. Here, managing an entire large farm, managing an entire city. That is the big difference between the CPSs of that time to the CPSs of today. Okay, so let me illustrate some examples of different kind of CPSs going back to the 70s and coming up to today. So this is a very well-known thing that many of us have at home, standing in the garage or driving around the city. There's a car with an internal combustion engine, and then there is the fuel tank, and then there are the various other things associated with that engine. And sitting here, what Bosch did, they introduced into that car, the motor car, a microprocessor back in the 1970s. I remember hearing about the microprocessors during my third year of my 5-year BTech degree in those days, around 75, 76. And just around the end of that decade, Bosch already introduced microprocessors in the motor car engine to control fuel injection. Okay? But there's one important difference between the kind of CPS this is and the kind of CPS I'll talk about towards the later part of my talk. You see what's happening out here? There's a microprocessor connected by a wire to every single device in the engine. There's a wire going all the way to the carburetor. There's a wire going all the way up to the spark plugs, a wire going all the way up to the fuel tank, a wire going all the way up to the fuel injectors. Okay? This is what is called a inference and control in a physical domain by tightly coupled sensing, computation, and actuation. The system and the computing are tightly coupled. There's a wire running from each sensor to the computer, and there's a wire running from the computer to each actuator. Okay? Now, for those who are a little familiar with networks, the model is this. There's a physical domain, there's computing, there's sensing, and there's actuation. And they're tightly coupled. There's a wire running between the sensors and the computing, and a wire running between actuation and the computing. This was the early Cpss, 1970s, the first application of microprocessors to control in an engine. The word CPS is more recent. They used to call in that time SCADA, which probably many of you may be familiar with, supervisory control data acquisition. In a system like this, where the computing and the control and the actuation are tightly coupled, this is called monolithic SCADA. So these are the old terms from the 70s and from the 80s, and the new term is CPS. Let's move on. What happened? Well, Bosch themselves realized that this kind of architecture is not very scalable. Because suppose now you want to extend that computer-based control to not just the engine, but you want to extend it to the drivetrain. Okay, you want to extend it to the engine, to the door windows, to bring them up and down, to security, and to the various other environment control module of the car. You have to then run from the computer wires everywhere. Ultimately, it turned out at some point of time that kilograms of wires were running in the motor car, and a good fraction of the car's weight was just the wires running from the computer to the various systems. So then Bosch invented at that time something that is still very well known called the Control Area Network Bus, CAN bus. And so now you have this copper wire running across the car. CAN bus was used also in the railways and ships. So there would be a wire running across the ship or the car, and you'll connect up all the engines and the drivetrain and everything to this bus, and now you have a shared medium, what is called in networking a shared medium bus, on which all the signals will flow and the computing and actuation will take place. So what does this become now? Inference and control in a physical domain. The physical domain now is the motor car, by sensing, computing, and actuation interconnected by a high-performance communication network. Okay? The key is high-performance communication network. Rather than having copper wire running from every point to every point, now you have a shared network. It's high performance. So in fact, now, again, perhaps if you're familiar with networking, what has happened is that earlier we had actuation, computing, and sensing. Now you're running this over a TCP/IP network. I mean, I think many of us nowadays know what TCP/IP means. So we're running it over a TCP/IP network. There's TCP/IP stack here, TCP/IP stack here, TCP/IP stack here, and in between there's a shared medium network. Okay? But the thing is that this network is very high performance, so the kind of load that the CPS puts on the network is very small. So one doesn't need to really care about network performance. If the performance of the network is high, we can think of the inference and control as separated from network design. This is a classical engineering approach of separation. We are separating the network design from the CPS system because the network is so fast, we don't really care about it. Okay? So this was the one evolution from hardwired networking, hardwired communication, to shared networking, but high-performance networking, so that you could still think of designing the CPS as separate from the network. Okay, and I'll tell you more about this as I go on. This was called networked SCADA. Okay, obviously from monolithic SCADA to network SCADA. Let's move on. Okay, now this is a bit of a fanciful slide, but I think it helps create the image in the mind of what CPS is in the 2020s or will be in the 2020s. Let's look at this. All of us have vehicles and all of us have seen tires, but probably very few have seen what's inside this tire. It's a tiny 1 centimeter cubed. It's called the Pirelli Cyber Tire. Pirelli is a famous tire company. It's called the Cyber Tire Sensor. Okay? The little 1 centimeter cube device has a lot of smarts in it. It is stuck to the wall of the tire. It can do a lot of very interesting things, which I'll explain on this slide. So first of all, the least it can do is give you the tire pressure level and give you on the dashboard alert, your tire pressure is falling very fast. So it has some sort of a sensor inside it, which allows it to sense the amount of pressure that's around it and declare to the dashboard the pressure is changing very fast, stop the car and look at your tire. But there's a lot more to it than that. The cyber tire sensor has in it a 3-axis accelerometer. An accelerometer essentially tells you acceleration in the direction of the axis. So we have 3 axes, you can get acceleration in X, Y, and Z axes. Okay? So it has built into that little device a 3-axis accelerometer. It's built into the little device a temperature sensor, pressure sensor, a wear sensor, and a revolution sensor. Okay? And it has in it a wireless communication module which permits it to communicate wirelessly with the dashboard and with the computer on the dashboard. Now, how did things come to this pass from the 1970s? And it came to this pass because of the advancement in low-power electronics, in integration, in small devices which are cheap and low power. Now, what about power? I'll talk about that in a minute. So what can this little device do? At the least, it can tell you this. It can infer road condition. If anybody has driven on a wet road just after it rains, you know that the car becomes a bit unstable. If you have driven on ice, it's even worse. Well, this little device can sense what's happening on the wheel and communicate with the computer, and the computer can then directly talk to the drivetrain and control the car. It can determine grip, it can warn about skidding, so that is the decision support, that is the inference part. It can actually go and take control of the car. It can take control of the drivetrain, apply brakes, and can adjust the speed and prevent the car from going into a skid. Okay? So how does this guy get charged? How do you get a battery into this? Well, there's a tiny rechargeable battery inside that, which is packed into the device. When the tire is thrown away, this is also thrown away. And when the tire is spinning because of the thrust from the engine, as the tire is spinning, this charges itself. I'm sure all of you have used those watches, which in the olden days, where because of the shaking of the hand, the watch gets charged. A very similar thing happens out here. You are recharging the battery in the little device through the spinning of the wheel. So now this was a very interesting concept. This particular device was released by Pirelli, I think in 2012. It's been about 10 years now. I do not think I have really seen this application. Maybe I'm a bit behind. Actually there in vehicles today. It is primarily being used for informing the driver about the condition of the tire. So what is it? What is this that stands between us and the huge possibilities in front of us? Here are the challenges. To design reliable, robust decision support and control based on wirelessly connected sensors and actuators. That's a big challenge nowadays. You have large systems, you have these devices embedded in the systems. From there to the computers are only wireless communication. And wireless communication, as we know, anybody who has used Wi-Fi, the signal fades, sometimes you don't even have signal. You say that no network and all those things. So all those problems with wireless are there with us. How do we design reliable systems where human life is at stake with this sort of a technology? That is the challenge. Now, although I've spoken about engines and cars, the new vision of CPS goes far beyond that. I think that will be the early applications of CPS. Already it's been happening. I've told you it's been happening for the last 50 years. But what's really exciting researchers like me and my colleagues in I.I.Sc. and many other places is this vision that these sort of systems will play a very important role in what are called socio-technical systems. What are they? Smart factories, building power management. There's an entire, maybe an apartment grid or an entire state grid, you want to manage that. Water networks, I know the quality of water we get in large cities nowadays, often contaminated. Well, can you monitor the water? Can we assure the user that the water that they're getting is of high quality? Can we detect leaks early? Instrumented cities, well, I can imagine that there is a water network, there's a road network, and there are emergency vehicles moving around. Can we have a CPS? I'll talk more about that later. Is there a CPS over the entire city which is somehow being used to manage it? And of course, I think this was a fairly early example of digital agriculture, managing large vineyards and farms through this technology. Okay. Now, my title of my talk said CPS for Industry 4.0. Okay, so what examples are there of that? So here are I'll give 3 examples of how CPS can be very useful for the industry. This being Shriram Institute of Industrial Research, probably you do deal with factories, and this may resonate with some of you. Now, an important fact is in an automotive factory, 64% of line stoppages are due to servo motor failure. Servo motors are these small motors which control the movement of arms and levers and so on and so forth. And even the motors which run these big machines. Now, if you could somehow, so what happens is if the motor fails, if the bearing fails, the line just stops. Often the line stops in a way that you can damage something in the line and that may take several days to repair what was damaged. Can we not install in the factory a Cps system which will give us in advance information that, look, something is going to go wrong, stop the factory, stop the machine, and take action before it is too late. So that is what is written out here. Monitoring the vibrations and looking for trends in the failure can help schedule preventive maintenance during natural downtimes between shifts and increase efficiency and throughput. I think you've seen that whenever, olden days when a train stops, somebody goes to every wheel and locks on the wheel. Well, why should you do that? You can't. It's not a very practical way of doing these things. Why can't we have a Cps system on the train or in these machines which will alert you about these problems much earlier than it is until they fail? Okay. A very important part about factories nowadays, given the new labor laws, given the importance we have for human safety and human life quality, is worker safety. So worker safety, I mean, there's a variable I'm wearing, this monitors my heartbeat, but you can do a lot more than that. With variable in video analytics, is the worker fatigued? Is the worker distracted? Are they taking more time than normal? Are they taking less time than normal? And hence are error prone. So some of these things can be monitored through various sensors on the human body, through the cameras that are facing the worker, and through a lot of artificial intelligence algorithms, which will make you infer from the data that you have that something is not right, we should take action on this now. Okay? Production line management. Now, production line management, if you talk to a traditional four person, you will probably, they have some sense of how the factory is working well, what not working so well, what can we do to improve the production flow. But can we do something what is called a digital twin? Can we take data from the factory, create a digital copy of that factory on the computer, and then be able to ask questions about that factory from the digital model? And that model is constantly updated using sensors from the factory floor, and that again is an example of how CPSS can be used in Industry 4.0. Okay, so I've now given you an idea of what the national leadership thought, what the history of CPS is, and I have given you some examples of applications of CPS. Now, what does it look like? It's somewhat more detailed. So here is an example of a traditional, what you would call a cloud-based CPS. Okay, cloud is a very common term nowadays. You have a physical domain, okay? By the way, what time do I have to? It's almost 5, but in the half an hour, it's okay? Okay. So, so this is a physical domain. As I said, there's so many possible physical domains, building or a farm or something. In the physical domain, we embed some sensors and embed some actuators. And then these sensors and actuators have on them wireless communicators, which can communicate to this relay, this little base station out here, which can communicate via several other base stations to the internet, okay, and from there to what is called the cloud, okay. So all the data from here goes across all this wireless network, the wireline network, and all the way to the cloud. The cloud has analytics in it. The analytics makes some decision about the domain, and the decisions are then fed back to the domain, okay. So for example, the decision could be there's an intruder, there's a crack developing, that particular plant is not doing very well. I'll give more examples of that later. So this I've already spoken about. I'll go a bit faster now. So the inference out here, so I'm going to often use the term inference. What is inference? Just to formally define it, inference is trying to conclude something about the world, about the state of nature from data. You collect data and you say something about the state of nature. Okay, something is not right, something is failing. So the inference can reside in the cloud, which is the current sort of common architecture. The inference could be brought to the edge. This is often called edge computing, often called fog computing, or maybe in places like a lot of pollution, smog computing. And then there is, this is the biggest challenge. Why should we send all the data from here all the way to the cloud? Why not stop it here and compute here? And why not compute in the domain itself? After all, these are smart devices. Each one of those little devices I showed you, like the one in the tire, has a small microprocessor, has a battery, You can make some decisions right there. Why not trust that, make some decisions right there, and send only part of the decisions up, and then even more decisions further up, even fewer decisions further up? That would be a very interesting architecture, which is, of course, a bit futuristic right now. So the challenge in sort of building all this, although it looks quite simple, but challenge in building all this is to build useful, safe, secure, privacy-preserving, provable, performable CPS systems. Every one of those words requires a new expertise. Okay, safety is one expertise, security is a different expertise, privacy is a different expertise, probability is a computer science expertise. My expertise is only in that little word out there, performance. Okay, so this requires a whole battery of people who work in computer science, electrical engineering, and communication engineering, who will be able to cover all the problems that I've listed out there to be able to achieve practical and useful CPSs. Now, to look at the evolution of CPSs themselves, the traditional application would be there would be a computer in the factory, and you would have various bulbs and lighting and fans and so on, and there would be a wire going to that. This is the old system. The current system that's evolving is what is called the cloud-based system. That is today, the cloud, and you have shared medium networking and so on and so forth. What I was talking about towards the end of the last slide was what is called distributed. That is, the decisions are being made by the vehicles and by the machines and by everything on the ground, and only a part of it is going to the cloud where more decisions are being made about it. Okay? So the traditional model is central, the current model is cloud-based, and the future model is fully distributed system of systems with local data processing and decision making. Okay? So I think I'm done with the high-level picture of CPS. Now, maybe I'll just go to the next slide. I have seen a lot of information technology evolve before my eyes since I finished my graduation in 1977. And I remember when I joined I.I.Sc., those were the early days of what were called local area networks. Everybody wanted to establish some network in the building to connect up the computers, to connect up even lights and so on and so forth, whatever they wanted to connect. And there were so many vendors out there, everybody sort of peddling their own proprietary product. And I think that many of us have made mistakes, bought something, and found that it didn't work too well, and then finally over time, standards evolved, and then you began to sort of conform to the standards. Well, in the area of CPS, IoT industry 4.0 landscape, this is what's happening today. It is probably like the situation that was in the area of local networks in the late 80s and early 90s. You see, every domain has a whole plethora of companies trying to sell their wares: home and building automation, manufacturing, industry automation, vehicular and transportation, healthcare, energy, cities, wearables, farming, and agri-food. And once you're locked into one vendor, you'll probably find that, okay, well, then the vendor will sort of keep on jacking up the prices and want to keep you locked more and more. This is the telecommunication domain, and again, there's so many standards out here. There's so many de facto sort of proprietary solutions out here, including, of course, Wi-Fi. So the way to cut the way out of this is to evolve international standards, which manufacturers will conform to, and then it will be easier for the consumer to be able to deploy a system for their own application. Okay, so how are things happening now? I mean, what is the future? So there is an international partnership which has been evolving over the last few years called 1M2M. Often you will hear the term M2M in this technology. IoT is a somewhat general term. When it is brought down to the industry, it is called machine-to-machine, because most of the applications of IoT are machine-to-machine communication. That's why you often hear the acronym M2M. So 1M2M basically means we'll have only one way of doing machine-to-machine communication. And there are these 8 standards bodies, 2 in the US and Europe. And in India, we have TSDSI. In fact, the head of TSDSI is sitting next to me on the front line, in the front row. And then we have the Japanese and another. And here are the various companies which have been, which have conformed, which have sort of aligned themselves with with this whole mission of building a 1M2M standard. So what is 1M2M? Let's talk about that. What 1M2M is? It's actually a very simple concept. I'll explain that. And I'll also explain, when I was talking about those 3 layers, something was missing out there. I'll bring what was missing here. So if you went out and you were to build an application, what application could you have? Here's an application for an emergency service that I want to build. I want to have an app on my phone to be able to call an ambulance or to be able to call a fire truck. Okay? Somebody gives me an application which will be able to do that. Somebody else gives an application for smart transportation. Okay? I want to be able to get a taxi. Let's suppose the following thing happens. Somebody in a family gets suddenly very sick. Now, what do you need? You need an ambulance. You need probably a paramedic. You need a taxi to take that family to the hospital. And you also need to be able to find where in the city of Bombay or in Delhi the roads are clear so that you can get the ambulance through and the taxi of the family, carrying the family through. You can see these are the three verticals. Okay, you have smart infrastructure. You want to find out where the corridors are free. You want to find out how to get a taxi quickly to my doorstep and how to get an ambulance to my doorstep. The silo-based approach creates a different CPS application for every one of those. And that is the way it is happening in the previous slide also. So what does 1M2M do? And by the way, if anybody has tried to install a smart home device, you can see what, you buy a smart bulb from Wipro, you buy a smart bulb from Y, they do not talk to each other. It's quite a mess. Okay? So this is the very simple evolution of this system, which is silo-based, to something where things talk across. There's a service layer. Now, I'll explain service layer very simply to those who are familiar with computers, which I guess all of us are. What's in a computer? In a computer, you have the hardware, you have your disk, you have your USB port, you have other things, you have your microphone, you have your camera. That's the hardware in the computer. Okay? On the top, you have applications. You use Teams, you use Zoom, you use Word, and you use all the applications which are there on your favorite computer. Okay? What's in between? You don't have to know that there is a disk in my computer. You don't have to know that there is and how it works. Standard services to application. Operating system do. Suppose you are concerned about accessing a microphone. I'll skip this. Into this 1M2M standard, I think taking the analogy of operating systems and the service layer being just like that in relation to the physical domain and IoT. It's too many bullets here, sorry for that. So I'll just quickly go over this. As I said earlier, modern CPS systems will have sensors and actuators all over the place. There's no question of running a wire from every point you want to check the illumination in this room to the computer, which wants to ensure that the room is properly illuminated. So everywhere you have wireless. So a lot of wireless technology is going to be used, is already being used. And wireless technology has been evolving from the early days. So in the early days, you would have small networks where you could use things like Wi-Fi, you can use Bluetooth. To the current time, vision is that 4G and 5G are going to be actuators that are required for CPS. Now, there's a challenge out there. Both 4G and the current evolution of 5G were designed only for high-speed internet browsing. Okay, the basic underlying technology was never designed to be meant for thousands of different sensors, each with a small amount of data, trying to access it randomly. You might not be aware of this, but when you pick up your phone and make a phone call, a lot of things happen between your phone and the base station. It's not visible to us, but it's happening out there. You can't do that for each little sensor lying on the floor or in a forest or in a farm. You have to make a very simple signaling. You have to allow for very small amounts of data to be sent suddenly. So that's the challenge. I think 4G has been addressing it using something called narrowband IoT. And 5G, I'll talk more about that in the next slide. 5G, okay, this is Wi-Fi. I think all of us know Wi-Fi. There's an access point. You can attach sensors to the access point, and again here, and you create, essentially like you connect your laptops, you can connect sensors as well, not too scalable. Similarly, you have something called ZigBee, which is actually quite popular nowadays in the industry for small installations. This is multi-hopping. So if there's a sensor here, the packet can go from the sensor to a relay, and then from there to this relay, and then up here, down here, and then to the cloud. Okay, so this is multi-hopping. This is single hopping. You see, there's a single hop from sensor to the access point. Both technologies are being used nowadays in practice in India in various installations like apartment, water management, and probably even in factories, but not too scalable, and performance is something of an issue. So what will 5G do? This is the 5G vision. This is the bigger vision of 5G. There's a triangle. You can view 5G as having a triangle defining the performance that it wants to address. This is the broadband services, internet browsing, you can say. This is machine-to-machine communication, or CPS IoT. And this is ultra-reliable, low-latency communication for communication which is small amounts of data at a high speed and very highly, at a low delay and highly reliable. We are concerned only about this side. Now look at the numbers out here. You want to have connections which are 1 million sensors per square kilometer. Very dense connections of sensors. For example, in a factory or a farm or a city. You want long battery life. You want that sensor which is put into the infrastructure to not require a battery change for 15 years. By then you can throw it away. Okay? So this requires the communication to be designed in a particular way where you can have devices, thousands of devices accessing randomly and being able to access with a very small amount of energy overhead and therefore being able to last for 1.5 decades. I think all I'll say about this is that there's no time for this. By the way, when this happens, when 5G and 4G come up to the point of being able to serve IoT and CPS, Wi-Fi will not go away, Zigbee will not go away. You will have what are called capillary networks. Just like in our body we have capillaries and you have the thicker veins and arteries, you will have the capillaries, Bluetooth and Zigbee and Wi-Fi, which then will feed data into the 5G and 4G or 4G and 5G networks. I think that's all I'll say about that here. Now, the last point, maybe another 5 minutes, I'll finish. The last point of my talk is somewhat research-oriented. This is the kind of thing that I do. I want to leave this with you to give you a sense. This is not just all about integrating well-known technologies. You can't just take a sensor from here and a battery from there and a Wi-Fi from here, put them all together, and it somehow just works. It will work. But the whole purpose is to make it work right, to make it work well. Just like we design a precision machine, you also need to be able to design a CPS IoT system. Let us see what the problems out there. I think if I convey this, probably is enough for me today. What is the issue here? So I'm still talking about the cloud-based architecture, where you have the domain. This is the domain, where you, as I said so often, city, farm, whatever, this is the domain. The domain contains sensors and actuators. From the domain, data goes over the IoT network, and from there it goes into the computer. Inference and control is done, and then this is fed back over the IoT network into the domain. Now, what happens? What are the problems that are faced if you do this? Of course, this is wireless communication. There's rate limitation. You can't send things too fast. Packet delay, the data that you send gets delayed. There's loss, as you know, when you are browsing, you know that often when you're watching a video or when you're hearing voice on Zoom or Teams, often the voice gets garbled in a similar fashion. Packet gets delayed, or there's loss. And the loss of time synchrony. If two packets are sent together, they will not arrive together. So in control, time is very important. You cannot fiddle around with the notion of time. So, but if you are doing things like this, called wireless networks, where there's delay, and delay is arbitrary, the notion of time is lost. Okay? So all of these things lead to these two questions at the end. How do we design these IoT networks, which could be from 5G, could be from 4G, could be Wi-Fi, Zigbee, to achieve a quality of service? Okay? I'm going to show you when somebody comes and deploys Wi-Fi in your building. That person will never be able to show you a quality of service. They will never say, okay, you will get at least 20 Mbps and no less. They cannot do that. That's not the way Wi-Fi works, and nobody will be able to do that for you. So how do you design quality of service into IoT networks is the first thing. How do you make sure that these deficiencies are curtailed, are as little as possible? But after you've designed the IoT network, you are living with the network. There's some network out there, whether it's Wi-Fi or Zigbee or 5G. Now you want to run the CPS on that. The CPS is running an expensive factory. How do you make the CPS work well? Well, now you have to design the CPS, inference and control, over a network which has deficiencies. The network will delay. Maybe it will delay less, but it will delay. It will lose data. It will have low throughput. So how do you now design, given a particular design of the IoT network, how do you design on top a CPS application which will suit the requirements of the CPS? The factory will not break down, and the workers won't get injured. I think I'll stop here because what I have to say next is rather technical. I think I'll close with the I'm giving an example out here from my own research of what happens if you have asynchrony in a network. And, okay, so I think all I want to say here is this. In all of this, I don't think I won't spend time on this. All I want to say here is this, that I think this point here. Those of us who learn these things and teach them, control systems, statistics, inferencing for control systems, have learned certain things in a particular way over the last about, I think, 70 or 80 years of this theory. But because of the issues I mentioned earlier, that you're now running a control system over a network, your data loss, data asynchrony, and such things, you have to rethink all those algorithms. So that's the only point I want to make, that network performance affects the optimal inference algorithm and its parameters. I mean, that's what I was doing out here. So essentially, you have to be aware of the network. You can't be network unaware. Okay, the network has to be understood, the limitations have to be understood, and then you have to design on top of that the CPS. So that is the new challenge. I think this challenge was recognized maybe about 1990s, but it's becoming more and more important as these things are getting deployed, and deployed in a way that they were never thought of before. So I think I'll skip all of this. Something even as textbook as Kalman filter, some of you may know about that, coming from the industrial engineering, has to be rethought, as this slide shows. Okay, my last slide. One keeps reading about this in the Gartner reports over the last 7-8 years. I don't know when it will turn out to be true. Network CPS are expected to become a multi-trillion-dollar industry for managing socio-technical systems. Smart factories, digital agriculture, urban water networks, and so on and so forth. Okay. The future CPS, or Industry 4.0 as an example, would involve a very large number of embedded sensors and actuators in the factory, in the domain. Okay? And therefore, we cannot run wires everywhere. It has to be all wireless, whether it's 5G, whether it is Zigbee or IoT or whatever. So necessarily requiring wireless networking for their interconnection. There are a large number of technologies for doing this which are available today, similar to what happened in the 85 to 95 time period, 30 years back. Okay. There are standardization processes underway to cut through all this mess. 1M2M is one such standardization process. It provides common services like the operating system of a computer. And you can run over a variety of communication and sensing actuation technologies, and thereby avoid creating silos and vendor lock-in. But on the research side, those of people who may be interested here on what is interesting from the point of view of research in this area, there are these problems of what happens when you run a CPS system over a network that causes packet delays, packet loss, delay variability, and so on and so forth. The well-known algorithms that we learn about in textbooks and that we teach do not work anymore. They have to be redesigned. And the performance of the algorithms are constrained by the performance limitations of the network. And there's also been some interest in the last few years of co-design. That is, you want to design the network and the CPS together. It's called co-design. And that could also be a way of doing this, but that, of course, is a bit harder to do. So I hope I've given you some sense of the area as it has evolved over the last 50 years and where it is heading today. And I don't think we see large deployments of it right now, but I'm told that it is the future, and certainly we work on this a lot. Thank you very much. Any questions or something? Any questions? Okay, sure.
You're welcome to ask questions. Yes, please. Gentleman in the front row, please. Yeah. Yes, please. You can use the mic.
Sir, my name is Dr. Sanjay Prakash Sahu. I represent a company called RJ Principal Knowledge Advisory. I have a PhD in Artificial Intelligence and Neural Network. We are talking about one of the subjects which I had done my thesis on. That time we never had this 802.15.4 Zigbee protocol. Currently what the industry standard of Industry 5.0 is envisaging is, if we can run a Pri-Fi network, that is a blockchain network, that is a generic, dedicated network based on a common service layer protocol using 5G telecommunication, high bandwidth, then all the signals that will cover is encrypted. So it will, when the signals are encrypted, the source and the destinations will be defined in the packet headers, along with the constituent data that each actuator, each relay is conveying, and each sensors are passing on to the main system. Plus, the copper network is a big inhibitor. So the switches, the RS-235 networking is being replaced by optical fiber. So if we combine the Pri-Fi network with optical network, that is hardware is the optical part, and the network protocol is the Pri-Fi network. Pri-Fi network is basically a blockchain network, the Web3 version of the network, running on the top layer of Industry 4. That is the solution which is being proposed in the 2021 August paper of National Science Foundation. So,
okay. I'm not so familiar with this Industry 5.0. I'll look it up. But you know, whether you run blockchain or you run security, ultimately runs on top of a physical network. Something has to move the bits. Something has to move the bits from point A to point B. Okay, if it's a blockchain on top, does not mean that you don't need a network below. So now the question that I can ask as well: what is the impact of communication network delays and packet losses on blockchain? Perhaps the answer to that is available. Here the point that I'm trying to make is, whatever algorithms you've designed in the optical networking or copper networking setup, where the communication delays are very small and very controlled, have to be rethought through, whether blockchain or whether control, whatever, if you're running it on wireless networks. That is the main point I'm trying to make. So I'll look up your point about Industry 5.0.
thank you, sir.
So can I ask?
Yeah.
I'm Dr. I. Bhattacharya from Quality Council of India. So we have been implementing the lean manufacturing in the industry, and now in the part 2, we are planning to go to the Industry 4.0. So now in your talk, you had said that the new standard with TDSI is coming is 1 M2M. So what is the current standard which is going on? Is it OPC UA we should say, or one has to move on to this 1 M2M from TDSI?
No, at present, I think the transition I'm talking about is from no standards, proprietary solutions to a standard. So there are, as I said in one slide, there are for different verticals, different companies are coming up with solutions, their own solutions. They'll have their own application, they'll have their own middleware, and they'll have their own even wireless layer. 1M2M does not constrain you from using the communication layer, your own IoT. It doesn't constrain you from building the applications. It gives you an operating system on which to interface between the applications and the IoT and the domain.
Thank you.
Good evening, Professor. Thank you very much for enlightening us on cyber physical system. So basically myself is Dheeraj. So I am from automotive industries. So this Cps system is already applied in automotive system as well as in the futuristic also. Maybe you are aware of OBD2 and OBD1 is also coming. So same system is applied on the automotive industries. But my question is a little bit different from the physical system, because maybe you are aware of a lot of health related issues is there, like water is polluted, air is going to polluted, food is also going to polluted. So this system is beneficial for the socio-economic system as well as or not? I just want to know.
Yeah, so in fact, the main thrust of my presentation was for those systems. As I said in the very beginning of my talk, managing the performance of an automotive engine or of a car with many things in it is a relatively simple problem. But managing the water supply in a city, managing the air quality in a city, managing a large farm where you want to minimize the amount of fertilizer you apply, pesticides you apply, and managing it economically and with high quality are the problems of today. So I think the future of CPS is actually in those problems. But I think that the first applications of CPS will probably be to the industry 4.0, and it will take some more time before it gets into farms and water supply systems in a big way, because it's a more challenging problem. There is a lot of embedded technology out there. There's a lot of difficulties in embedding sensors in a city. So I think the intermediate step would be to go to Industry 4.0, to the industry, from small systems like machines and engines to the industry, and from there it'll move on to systems like you're describing.
Thank you very much.
Yeah.
Thank you, sir, for giving us an in-depth view of the practical implementations of cyber-physical systems and the role that they play and will play in modern industry through your scholarly and thought-provoking lecture. We are obliged to Professor Anurag Kumar for sparing his valuable time to share his vast knowledge with all of us today. May I now request Dr. Mrs. Manju Sharma to present a memento to him. Thank you, madam. Employees are a valuable asset of any organization. In line with the tradition of Sri Ram Institute, to honor the employees who have rendered several years of yeoman service to the institute, we will now be presenting long service awards. There are 92 awards in all, including all those who became eligible in past 2 years when Founders Day celebration was put on hold due to pandemic situation. Today, we would be felicitating only those who shall be receiving this award for the last time before the next Founder Memorial Lecture. All others would be felicitated in a separate ceremony at the Institute. I request you all to remain seated as your presence will be a great motivation. May I now request Shri Alok B. Shri Ramji to present the Long Service Awards to the employees. Mr. H.C. Bhatt, an executive with a long work experience in Metal and Mineral Division. Mr. John George, having expertise in radiation processing of materials. Mr. R.K. Tiwani, a scientist experienced in petro products. Mr. A.K. Kaushik, an executive working in commercial section. Dr. R.K. Singh, a scientist with expertise in rubber and polymers. Dr. D.S. Chatterjee, having expertise in the area of environment protection. Thank you very much, sir. In order to express our sincere gratitude to the speaker and all our guests, I now request Sri Vijay Sardana ji to propose a vote of thanks.
आप सबको मेरा प्रणाम। आज इस मेमोरियल लेक्चर में प्रोफेसर अनुराग कुमार जी का लेक्चर सुना तो बचपन में जो हम लोग साइंस फिक्शन पढ़ा करते थे और आज साइंस उसको रियलिटी में बदल रही है। सो ये जो बदलाव है पिछले 30 साल में, फिक्शन टू रियलिटी, एंड दिस इज द आउटकम ऑफ रिसर्च। एंड आई थिंक दिस इज वेयर द श्री राम इंस्टीट्यूट फॉर इंडस्ट्रियल रिसर्च is there for the society, that whatever the challenges we are facing in different walks of life, in various sectors of industry, at Shri Ram Research Institute, we are here to address those challenges. आप में से बहुत सारे लोग यहाँ जो हैं और जो ऑनलाइन इस प्रोग्राम को देख रहे हैं, इस बार पूरा टेलीकास्ट लाइव हुआ है, बाहर भी बहुत लोग देख रहे हैं। उन सब के लिए मैं ये कहना चाहूँगा कि श्री राम इंस्टीट्यूट में करीब 40 ऐसी लेबोरेटरीज़ हैं। ये हिंदुस्तान में अपने आप में एक यूनिक कैंपस है, जहाँ पे हर सेक्टर पे जो करंट चैलेंजेस हैं उस पे हम लोग काम करते हैं, और आने वाले समय में क्या चुनौतियाँ इस समाज में आएंगी, इस देश को आगे बढ़ाने के लिए, समाज की भलाई के लिए, उस पे बहुत तरह का रिसर्च का काम हो रहा है। अब हर चीज़ को हम यहाँ शायद एक्सप्लेन नहीं कर पाएंगे, इसलिए मेरा आप सबको निमंत्रण है और अनुरोध है, जब भी आपको टाइम मिले आप इंस्टीट्यूट आएँ, बाकायदा आप फ़ोन करके अपॉइंटमेंट लेके आएँ, ताकि आपको वहाँ पे गाइड करने के लिए कोई ना कोई साइंटिस्ट ज़रूर रहेगा। किस तरह से हिंदुस्तान में एक वर्ल्ड क्लास इंफ्रास्ट्रक्चर एक 10 एकड़ के कैंपस में अंडर द गाइडेंस ऑफ गवर्निंग बोर्ड्स बनाया गया है, जिसने भी देखा है आज तक उसने कहा हमें उम्मीद नहीं थी कि इतना वर्ल्ड क्लास इंफ्रास्ट्रक्चर हिंदुस्तान में होगा। ये मैं आपसे इसलिए कह रहा हूं कि कुछ चीज़ें हम एक्सप्लेन करते हैं, जैसा अभी प्रोफेसर अनुराग जी ने जो एक्सप्लेन किया, जो बताया, शायद स्लाइड्स में वो इतना कॉम्प्लेक्स लगता होगा कि इतने सारे सर्किट्स हैं, कैसे डेटा ट्रांसमिट होता होगा, लेकिन जो लोग उस सिस्टम्स में काम कर रहे हैं और जिस तरह से उस सिस्टम को बनाया जाता है और उससे जब आउटकम आता है, उससे जो एक सेंस ऑफ सेटिस्फैक्शन मिलता है उस क्रिएशन से, उसको डिफाइन नहीं किया जा सकता, क्योंकि यू आर चेंजिंग द फ्यूचर ऑफ सोसाइटी एंड द नेशंस। मैं आप सबकी तरफ से, इंस्टीट्यूट की तरफ से, बोर्ड ऑफ गवर्नर्स की तरफ से प्रोफेसर अनुराग आपका बहुत बहुत आभारी हूँ, धन्यवाद करता हूँ कि ये 2 साल का इंतज़ार सफल रहा। हम शायद इस चीज़ को अगर आर्टिकल के रूप में पढ़ते या कहीं किसी मैगज़ीन में पढ़ते तो शायद इतना एक्साइटिंग नहीं होता, जितना आपने उस चीज़ को, हर साइंस को एक रेलेवेंट पॉइंट से सोसाइटी के साथ जोड़ के जो बताया। और शायद टाइम कम था, जो बाकी की कुछ स्लाइड्स रह गई, मुझे लगता है कि हम सबको इन बातों पे ध्यान देना पड़ेगा। और सबसे अच्छी बात ये रही कि ये ऐसा नहीं है कि वी आर टॉकिंग ओनली अबाउट इंडस्ट्रीज। प्रोफेसर अनुराग सेड वेरी क्लियरली दैट वाटर क्वालिटी, एयर क्वालिटी, फूड क्वालिटी, मेडिकल सिस्टम्स, our own vehicles, small things which we are doing, even smart switches and plugs which we are using in homes, everything is actually part of this revolution. And this is just a beginning. Because the most important thing what he mentioned is कि जैसे 1970s के अंदर हर कंपनी अपना एक कॉन्सेप्ट और मॉडल लेके आई थी, स्टैंडर्डाइज नहीं था। जब वो स्टैंडर्डाइजेशन हुआ तो एक कंप्लीट इंटरनेट रेवोल्यूशन आया। तो मुझे लगता है साइबर सिस्टम्स पे जब स्टैंडर्ड्स बनेंगे और जिस तरह से उसमें डेवलपमेंट आएगी, दिस विल बी ह्यूज अपॉर्चुनिटी फॉर कंट्री लाइक इंडिया एंड टैलेंट ऑफ इंडिया। लेकिन अब ये हमारे ऊपर है, जो हमारे यूथ कॉलेजेस के फ्यूचर ऑफ इंडिया वहाँ बैठे हैं, अब आपके लिए है कि आप उस तरह की स्किल्स को अपनाएं, डेवलप करें, ताकि समाज आपकी काबिलियत का फ़ायदा उठा सके। इस इवेंट को ऑर्गेनाइज करने के लिए बहुत लोगों ने कंट्रीब्यूट किया। टू स्टार्ट विद आवर चेयरपर्सन जी ने हमें गाइड किया कि किस तरह का थीम इस बार हमको रखना चाहिए। अनुराग जी को उन्होंने रिक्वेस्ट किया आप सबके सामने लाने के लिए, और उनके मार्गदर्शन में और बोर्ड के मार्गदर्शन में आज ये पूरा प्रोग्राम हुआ। ये बात हमें समझनी पड़ेगी कि 1947 में श्री राम इंस्टीट्यूट फॉर इंडस्ट्रियल रिसर्च की स्थापना हुई थी। ये वो समय था जब देश आज़ाद हुआ था। आज हम अमृत महोत्सव की बात कर रहे हैं। 1947 में इस देश में हम फूड सिक्योरिटी कैसे इंश्योर की जाए उस बात की चिंता कर रहे थे कि लोगों को खाना कैसे मिले। और उसी समय एक विजनरी थे हमारे बीच में जो इंडस्ट्रियल रिसर्च के बारे में सोच रहे थे कि खाना तो शायद हम कर लेंगे, लेकिन हिंदुस्तान का भविष्य अगर इंडस्ट्रियलाइजेशन वर्ल्ड क्लास नहीं हुआ तो शायद सिक्योर नहीं होगा। हम सिर्फ खाना खा के देश की तरक्की शायद ना कर पाए। अब वो जो विज़न था 1947 में लाला श्री राम जी ने जो रखा था, आज वो इंस्टीट्यूट जिसके हम लोगों को अपनी सीखने का मौका मिलता है, वहाँ काम करने का मौका मिलता है, बहुत कुछ वहाँ एक्टिविटीज़ हो रही हैं। मुझे लगता है कि इस बार जो बोर्ड ऑफ गवर्नर्स ने चैलेंज रखा है इंस्टीट्यूट के सामने, और मैं आपके इसलिए कह रहा हूँ कि यू शुड फील हैप्पी एंड प्राउड कि वी हैव डिसाइडेड टू ensure that Shri Ram Institute for Industrial Research should become a jewel of India. हमें हिंदुस्तान में इस इंस्टीट्यूट की वो गरिमा लानी है और हिंदुस्तान की तरक्की में हम अपना पूरा योगदान देंगे। ये हमारे साइंटिस्टों का कमिटमेंट है। करीब 350 साइंटिफिक स्टाफ हमारे साथ काम करता है और बहुत सारे लोग आते हैं जो ट्रेनिंग लेके जाते हैं, और इस इंस्टीट्यूट की अपनी एक क्वालिटी सिस्टम से क्रेडिबिलिटी है जो 75 साल से इंटैक्ट है और हमेशा रहेगी। इस इंस्टीट्यूट के और इस प्रोग्राम में जो फाउंडर्स लेक्चर, मेमोरियल लेक्चर जिसको हम बोलते हैं, साल में हम एक करते हैं। ऐसे 4 लेक्चर हम और करते हैं जो बंसीधर जी के नाम पे होते हैं, हर क्वार्टर में एक। और मैं आप लोगों से निवेदन करूंगा, जितने लोग यहाँ हैं और जो इस प्रोग्राम को देख रहे हैं, कि अगर आपको लगता है कि कोई और इम्पॉर्टेंट टॉपिक है जिसमें हमें बंसीधर जी के मेमोरियल लेक्चर पे आप लोग सुनना चाहते हैं किसी एमिनेंट पर्सन को, प्लीज़ सजेशन दीजिए। क्योंकि एक हिंदुस्तान में श्री राम इंस्टीट्यूट फॉर इंडस्ट्रियल रिसर्च हम सिर्फ लैब तक नहीं, साइंस को आम आदमी से कैसे जोड़ा जाए और नई आइडियोलॉजी को आम आदमी तक कैसे पहुंचाया जाए, साइंटिफिक आइडियोलॉजीज़ को, हम इसको भी एज ए कम्युनिकेशन अप्रोच सीरियसली लेते हैं इस बात को, और हम उसको करते रहेंगे। फॉर्मल वे में धन्यवाद देने के लिए वंस अगेन अनुराग जी आपका बहुत बहुत धन्यवाद। मैडम चेयरपर्सन एंड बोर्ड ऑफ गवर्नर्स आपका बहुत बहुत धन्यवाद, आप लोगों ने टाइम दिया। कमानी ऑडिटोरियम और मैनेजमेंट का बहुत बहुत धन्यवाद। इंस्टीट्यूट में आपको ये लगा होगा कि यहाँ जितना अरेंजमेंट हुआ है, शायद पता नहीं आपको, एवरीथिंग इज़ डन बाय आवर ओन स्टाफ मेंबर, इंक्लूडिंग द डिस्प्लेज, द प्रोडक्ट विच आर डिस्प्लेड। हमने बहुत थोड़े प्रोडक्ट दिखाए हैं क्योंकि स्पेस नहीं है, लेकिन अगली बार आएंगे आपको और बहुत कुछ देखने को मिलेगा। सारे स्टाफ को, सपोर्टिंग स्टाफ को बहुत बहुत धन्यवाद। और जो बाकी एजेंसीज जिनको हमने हायर किया सपोर्ट करने के लिए, चाहे वो कैमरामैन हो, मीडिया पर्सन्स हो, बाकी जो अरेंजमेंट्स किए हैं लोगों ने, ट्रांसपोर्टर्स, जितने लोग डायरेक्टली इनडायरेक्टली इस प्रोग्राम को सफल बनाने में जुड़े, उन सब का धन्यवाद। इन सब के बाद मैं अंत में आप लोगों से ये कहना चाहूँगा कि अगर कहीं आपको कोई रिसर्च चैलेंज दिखता है कि ये समाज में एक चैलेंज है, इसका एक साइंटिफिक और टेक्निकल रिसर्च आंसर होना चाहिए, प्लीज़ फील फ्री टू सेंड इट टू अस। ये इंस्टीट्यूट इस समाज, इस देश को बनाने के लिए स्थापित किया गया था और हम इसका रेलेवेंस हमेशा बनाए रखेंगे। इन शब्दों के साथ आप सब आए, आप सब लोगों ने टाइम निकाला, आप सबका बहुत बहुत धन्यवाद।
With this, we have come to the end of today's program. We hope that you have enjoyed the program and will again oblige us with your gracious presence in the Founder Memorial Lecture 2023, which would be the 57th in the series. Wish you all good evening. May I request you all to join for refreshments. Our volunteers will escort you for the same. Thank you.